Well, hello and welcome to Mr. Robbins back here with you on the brand new exciting video, all math-based, of course. And as always, it is an honor and privilege to be serving you here today, as it is every day here in my virtual classroom. And I sure hope it'll be an honor and privilege today because, boy, we got a lot of problems to do. And this is going to be all in logarithms, logarithm properties, logarithm equations, and such. And I'll tell you what, once I start teaching something and I do it once, I'm going to have to go a little bit faster because these are going to be a while. There's a plethora of problems. If I'm right to attach a PDF for you, I will do so. There are problems that will be skipped when it comes to like number sets. You're going to go like, why are numbers missing? Where are the numbers? That's because I'm skipping problems just to save any semblance of time that I can. So it's an honor and privilege. Let's go ahead and get started. So right here, we're going to go ahead and start with expanding and condensing logarithms together. This first page is all about expansion of logarithms. To expand a logarithm, and I'm jumping right into some of the properties, guys, just giving you the formula straight up. There are three in particular, four, I don't know, there are a lot. To expand a logarithm is to write each term and each factor of each term without any exponents as its own separate log. So there are some properties involved, such as when you have a product inside of a log, the log of some product. You can separate those into two separate logs of the same base, like this. Now this works the other way as well, and that'll be important when we do condensing. This is also true for taking the log of a fraction, and you end up subtracting those logs there. Now, if you remember what logarithms are, the result of a logarithm is an exponent. So this should sound a little familiar to some of the properties that you've done in the past. That would be something like this. That was totally wrong what I just wrote. X to the m times x to the n equals x to the m plus n power. You can see where those exponents add. Well, here exponents add, and I say exponents because the result of a log is an exponent. So, it's that kind of thing that's coming into play. That's actually happening here. A third big one that's going to happen with expansion here is when you have something inside that is an exponent inside of a log. We're going to take it and pull it out in front right here, and it's going to be multiplying by the log instead. If the result of a log is an exponent and there's an exponent inside the thing that we're taking the log of, then let's get that exponent result out like that. There's some other ones that'll jump into play. They're not necessarily logarithm based though. Like for instance, radicals can convert to fractional exponents and things like that. But in expanding logarithms, we're going to write as many logs as we possibly can for the problem. We're not solving anything. It's just an expression. We're just getting this as fully expanded as possible. And there are benefits to it that we will not outright see here, mostly because a lot of them can't be evaluated by hand, and a lot of them have variables. So you won't see the benefits for why we might do it, but they do have some. And just knowing the properties is going to be a part of understanding what you can and can't do for logs. Condensing is almost just as beautiful of a notion for other actual use. So let's go ahead and expand each logarithm here. We start off with a natural log, and it's okay to be a natural log of something. Remember, this is a product. That means log base e. This is a product, x to the 6 times y cubed. So let's split this up into natural log of x to the 6th plus natural log of y cubed. That's using this first property here. Now I'm going to use this third property here where I have exponents inside of these, the 6 and the 3. I'm going to pull them out in front of each natural log here. And that'll be 6 times natural log of x plus 3 times natural log of y. And that is a full expansion of that one right there. And we are done. So you can see that I didn't pull them out to begin with because the 6 only applied with the x, the 3 only applied with the y. And that order of operations thing says that needs to kind of, that's treated just with x and y. The product is kind of what happens after you raise those to those powers. So we split the product first into the sum, and then we do that. Okay, number 2, log base 8 of those the three terms, right, the three factors right there. So this becomes log base 8 of x plus log base 8 of y plus log base 8 of z cubed. These are all taken care of as best as they can. The z cubed is going to become a 3 multiplied in front of that thing right there. And at some point you're probably going to start seeing me just skip that step in between, and I'll say it with you as you start to understand, well, wait, where did that come from? Well, it came from doing exactly that. The previous step before being a z cubed, pulling the 3 out in front, and that is your final expansion. You're pulling out as much as you can out of each log, and you're creating as many logs as possible. That's basically my definition of how you expand logs. My definition of condensing logs is going to be a lot easier with that. Now, number 3, so this to the 4th power thing, you do have to understand that it is for the thing you're taking the log of. That means that 4 is within this whole exponent. Now, like exponential properties had simplification rules and understandings and ways that we did it, I always said there's more than one way to do that problem. There's more than one way to do this problem as well. You could take that 4 and apply it to those parts right there. I wouldn't recommend it. I know that it's something that, you can do. You'll still get the right answer. Like, I'm not going to do 3 cubed right now either. My whole goal is to get as many things taken out of logs as possible. Anything that can be treated as an exponent, we get out of there. So I'm going to start with that 4 immediately, get it out of here, and multiply it by the log base 9 of 3 cubed over 7. And because there's a fraction inside this log here, we will be subtracting these 2 sets right here. So this is 4 times, now remember, it's both parts of this log here, so I'm going to put that in parentheses, log base 9 of 3 cubed minus log base 9 of 7. 4 is multiplying by both of those, right? Not just one of them, it's that whole thing. So you can distribute the 4 into both of those. I shouldn't have any parentheses in this thing outside of what I'm taking the log of. And we got to pull the 3 outside of this as well. So what happens when you pull a 3 outside of the log and you multiply 4 by that log? That's 4 times 3. So right here, instead of just writing 4, instead of just writing 3, I'm going to write 12. Hopefully that makes sense, doing those in one step just because of my space. Log base 9 of 3 minus 4 is distributing there, 4 times log base 9 of 7. And this would and should be a good final answer, but I'll tell you what, I do know that the log base 9 of 3 is 1/2 because 9 to the 1/2 power is 3 because the square root of 9 is 3. So that should just be 1/2, and 12 times 1/2 should be 6. An alternative answer to this is 6 times minus 4 times log base 9 is 7. But I'm guessing that their ultimate telling for you is let's just expand it and not evaluate something. But here's one of the reasons why you can, here's one of the benefits to it, is when you can do things like this, you can actually take care of it. So there's that one. Okay, number 4. So it's that same kind of thing as number 3 here. Now let's try the alternative. Let's go ahead and try and cube. Let's cube x cubed and cube y. At least it's not going to change anything else within there. So let's start by not expanding yet. Let's just do log base 7 of x to the 9th over y cubed. Remember those 3's multiply and y cubed is y cubed. So now we turn it into a subtraction here. That'll be log base 7 of, oh, hold on. You want to do 2 steps in one this time? Can you guys do this? The 9 that's going to pull out with the x is 9 times log base 7 of x minus, pull the 3 out, 3 times log base 7 of y. Like I said, at some point, I'm going to have to speed up for myself here. And this might be one of those moments where I'm going to do exactly that. You might go, whoa, hey, wait a second. Where'd you get those from? I kind of did 2 steps in one on that one. And it's based off what you just saw previously. And I think I'm going to do some of the same for these here. Number 5. Selfishly, guys, you want to see how many problems we got? 36. And then these, you can see I skipped problems. See 121, 122, 127, 128. And then these problems. And then these problems. So we got a bunch. You can see why I'm going to speed up on some of these. Hopefully they start to kick in. All right, number 5. This is actually the majority of them. Log base 8 of these right here. So it's very similar to number 1, I think. So I'm going to pull out the 6 in front of A's, log base 8 of A, and pull a 5 out in front of there. This, literally, I'm giving you the answer on that one there, but it becomes an addition because this was a product right there. Okay. Same thing with this one here. This is another product and it becomes addition. I can pull the 3 out of the one where you take the log of 6. And then 3 out of where you take the log of 11. So this is going to become 3 times log base 4 of 6 plus 3 times log base 4 of 11. Again, the plus here because this was multiplication, the product inside the log there. Okay, I'll go a little slower on this one here because the exponent out there. So the squared thing, I'll pull the 2 out in front again this time. So this is 2 times log base 3 of u cubed over v, which is 2 times, I'll distribute the 2 right now into both of these. 2 times log base 3 of u cubed minus 2 times log base 3 of v. And again, it's a subtraction because the division inside there are only so many times I can end up saying that. I'm going to pull this 3 out in front. It's going to multiply with the 2. So it'll be 6 times log base 3 of u minus 2 times log base 3 of v. And that is your final result. Okay, number 8. The natural log of the cube root, not cubed, the cube root of u and v and w. So when you take the cube root of something or anything raised, the nth root of it's going to be to the 1/3 power. So what happens is this is all to the first power here, and it's the cube root. That 3 exists as the denominator here. So this becomes the natural log of u times v times w raised to the 1/3 power. It is that 1/3 that is going to come out and multiply in front of the natural log of u, v, w. So multiplying by 1/3 also means dividing by 3. We are going to divide what will become a sum of 3 natural logs by 3. The natural log of u will divide by 3, because that's times 1/3. The natural log of v will divide by 3. And the natural log of w will divide by 3. Now you might ask, can you still write a 1/3 in front? Of course you can. I just believe that this is what we're going to be seeing later, and I believe an answer key will say that. So that's why I'm writing it. But of course, you can write 1/3 in front of all 3 of them. Just make sure that you do in front of all 3 instead of just, in parentheses for them. Okay, number 9. Log base 6 of 3 times 2 times 5 to the 6. And again, we're not doing 3 times 2. We're not changing. We're stripping as much out as we can. So this becomes log base 6. They're asking you to not evaluate anything. They're saying expand property-wise. Doesn't matter if it's number or variable. This becomes log base 6 of 3 plus log base 6 of 2 plus 6 comes out for the 5, right? 6 times log base 6 of 5. Are there any ones with products and fractions together? It looks like they don't have fun. Number 10. There's no difference. Log base 4 of 2. You can do log base 4 of 2. That's 1/2. I'm not going to. Plus log base 4 of 11. Plus, pull the 4 out. 4 times log base 4 of 7. Yeah, not much for me to teach on some of these ones, right? Eventually, it kind of repeats the same stuff. Number 11. This one has that a to the 1/3 cube root of a, right? That becomes a to the 1/3 power. So this, I'll just rewrite that as, well, let's log base 6 of c to the 5th plus log base 6 of a to the 1/3. And again, you want to write it in its exponential form so you can pull it out properly. I'm not going to pull a 3 out, but a 1/3 out. And I'm going to pull a 5 out of this one. So 5 times log base 6 of c plus, and remember, 1/3 times something means that something divided by 3. So log base 6 of a divided by 3, like that. Okay, natural log of 5 squared over 2, all raised to the 5th power. So all of that right there, I'm going to go ahead and take that 5 and pull it out, and that becomes 5 times, I'll pull it out in front of them right now, natural log of 5 squared minus 5 times natural log of 2. So the subtractions from that division right there, let's pull the 2 out, multiply with the 5, that becomes 10 times natural log of 5 minus 5 times natural log of 2. Full-on expansion. And try some of these in your calculator, especially the number ones. Go ahead and try it here. I got to use the calculator later, so let's go ahead and type it in now here. Let me graphing calc. I'm going to pull this up right now. let me type in natural log, and here's where them not using parentheses is important. Where is it? Natural log. I got to use parentheses here. 5 squared over 2 raised to the 5th. But I got to make sure that it's inside the natural log parentheses as well, right? Them not using it's really important. Anyway, that value is this number here. Now let's try 10 times natural log of 5 minus 5 times natural log of 2. Let's make sure that it's the same value there. Okay, so we get that same number, right? Now, the last thing on this is, let's say that I wrote natural log of 5 squared over 2 raised to the 5th power. Here's where the difference is, and here's where it gets a little interesting. This isn't going to be the same number. Why isn't that the same number as the ones before it? Well, because is my calculator blurry? I'm sorry if my calculator is blurry on the screen. I think I know why, and I'll have to address it in another video. My resolution thing has changed right here. But anyway, I'm sorry, what was I saying? Oh, the number's different here because it's this last one. The 5th power is not inside what we're taking the natural log of. You're taking the natural log of some number, and then you're raising it to the 5th power. This, we're raising something to the 5th power, and then we're taking the natural log of that. And that's what this problem is really supposed to be. It's that first one. That's why when they don't use parentheses, that's why you always see me write these square bracket things right here. It's very ambiguous as to what are we doing? Are we doing this? And I'll tell you the answer is, what it is. We're not raising this to the 5th power. We're just raising this to the 5th power right here. Excuse me. We're raising. We're not raising this to the 5th power. We're just raising this to the 5th power. So we're taking the natural log of this whole thing right there. Otherwise, that 5th power thing won't go there, right? Now, you're learning a property with this stuff, right? Don't suddenly start taking some sort of x squared and say, I'm going to put it in front of the x and say it's the same thing as 2x. No, x squared and 2x are not the same thing. What we're doing with logarithms is a way different story. It's just like how x to the negative, it's just like how negative 2 isn't the same thing as 1/2. And you might be wondering, where the heck is that coming from? Because x to the negative 2nd power is 1 over x squared. There's a difference between exponential properties, logarithmic properties, and like the real world number things that we do. So I just want to make sure that you know that. And I promise somebody's going to do it for one of my students, and I'm going to say, are you no okay, here we go. Now we have this now I slowed myself down on that. I had to give myself that teaching moment to show why I keep doing this bracket thing. See if we can do all this in one step by talking it through. The division inside the log means it'll be a subtraction of 2 logs. We're going to do that. The 3 is going to pull out in front of the one with the x, and the y won't have anything pulled out in front except for that 6. The 6 is going to multiply by both of those. So everything's going to become 6 times larger. Instead of 3 times log base 5 of x minus log base 5 of y, it'll be 6 times 3. 18 minus log base 5 of x minus 6 times log base 5 of y. So the subtraction, the 3 that pulled out in front of the x, and the 6 that multiplied by both of them. That's your result. Number 14. This is a lot like this one right here. So what's going to happen is the cube root of 2 is also 2 to the 1/3 power. And we could really mimic this pretty much straight up. This is going to be the 3 pulling out in front of 7's log. 3 times log base 4 of 7. It's a product, so we are going to be adding. And the 2 to the 1/3 power, a 1/3 will come out in front of root of 2's log, not root 2, but 2's log, which is the same as dividing by 3. So log base 4 of 2 divided by 3, which I'm really compelled to turn this into 1/2 times 1/3, which is 1/6, but I won't. I just won't, because I just don't think they want us to expand further than we need to, or do anything further than expansion, I should say. Okay. Yeah, it doesn't necessarily get any harder here. It really is. I should have crossed some of these ones out, even for my own students. All right, so this is a lot like, I think it's like number 2 or something like that. It's log base 2 of u plus log base 2 of v plus 2 times log base 2 of w. All right. So right here on number 16, the 6 is, of course, inside the log. It'll pull out in front here. This is 6 times log base 9 of 12 cubed plus 6 times log base 9 of 7. And that 3 will multiply by that 6 to get 18 times log base 9 of 12 plus 6 times log base 9 of 7. And one more down here. It literally, is that literally a duplicate of this problem here? Pretty much every which way it's a duplicate, only instead of a 6, it's a 9. I mean, I don't even know what to say here. These are from a website. All right, so log base 9, 5 times log base 9 of C plus log base 9 of A, all divided by 3. Okay, so we're going to condense pretty soon. I got 3 more. We're going to condense pretty soon here. If you ever want to fast forward, if you think you got it, keep moving forward. You know the 4 is inside the log, right? So I'll pull the 4 out in front. It's also going to multiply with that 5 that pulls out in front of the x. So that'll become 20 times log base 7 of x. Now the 4 just goes in front of that y's log plus log base 7 of y. If there's anything you're getting out of this, hopefully, as I'm saying them out loud, it's how you say these properly. It's not log to the 7th power times x. That is as far away from anything that's math related as you can ever get by saying all those right numbers. Log to the 7th power times x, no. 20 times log base 7 of x plus 4 times log base 7 of y. And we did a lot of things with logs in the past. We'll be doing some with equations outside of these ones here. This whole worksheet is not just expanding and condensing. I hope you know that. But after the condensing, which actually should go shorter because I have to write less. But after the condensing part, we're going to do parts with equations. And I think maybe all equations the rest of the way. I can't remember. I think so. But what we've done before with converting properties and doing things like that, their actual log use, I think we'll give more use to. All right, log base 7 of z squared times the square root of x here. Remember that square root of x is x to the 1/2 power. Let's go ahead and write that to start. So as we split this thing up into a sum of 2 different logs, the 2 pulls in front of z's log. I don't know if that's correct to say z's log, but I hope you know what I mean when I'm doing that. And then 1/2 power that multiplies in front, I'm going to go ahead and divide it by 2. Like so. And there you go. And then lastly, not much changes here. This definitely looks like a problem we've done before. Log base 8 of u plus log base 8 of v plus 5 times log base 8 of w. All right. Okay, so that was expanding. Now, condensing goes the opposite approach. So if you remember these, not if you remember these, we've been doing it the whole time, but if you use these 3 properties in play right here, going from what you see on the left to the right is considered to be expansion. So this in blue is an expansion, expansion, expansion. While condensing is the other way. It's going what's in green here, condensing, condensing, condensing. Ultimately, what we're going to do is take what all the things that we're going to see appear to be in expanded form as far out as possible, really to the extent of what you saw us do. And we are going to then condense them into what we can, which is for the most part just going to be a single log. And you can only make it as a single log if they all have the same base. And of course, if they go from a sum, a difference, or any constant multiplied in front of that log. So you'll know when you're done in these ones a little more easily because you wrote it into a single log. That's basically it. It doesn't mean it's easier to do, but there might be less writing and you'll know when you're done. So what happens in this first one here is I have a 2 times, oh, and you know what I don't like is they don't use parentheses around these things here. Yeah, I've kind of mentioned that, but now they really don't around single terms. 2 times log base 6 of u minus 8 times log base 6 of v. What's going to happen is we're going to now kind of suck things back in. So now the 2 is going up into the log's exponent right here. That'll become a u squared, and this will become v to the 8th power. So this becomes log base 6 of u squared now as we condense minus log base 6 of v to the 8th power. And again, there's validity. There's a lot more validity in this that I can see when it comes to equation solving. there are times when you can evaluate that can help you here. And there's a lot more validity the other way when it comes to evaluating certain numbers or something of that nature. But there's that. Excuse me. And now we have the subtraction of two logs with the same base. That means this can turn into log of this single base here of a fraction of dividing these two like that. And that will be your final result. So we're going from expanded form to what's now that condensed form. As in, if I asked you to expand this, we should have gotten that answer. Subtract first, pull the numbers out in front. So you'll see a lot of that with these, to the extent that I'm already ready to write these in just one step and just give you the answer. But for a couple of them, I'll just help you out. So right here, I'm going to bring the 8 in with the a, log base 5 of a to the 8th power. Now this plus here will end up having us multiply log base 5 of b squared. So now this will lead to a product, log base 5 of a to the 8th times b squared. And there we go. And yep, I think already at this point, I'm now ready to start just going one step here. Pull the 8 in with the 12, the 2 in with the 5, and multiply the 12 to the 8th and 5 squared. So log base 3 of 12 to the 8th times 5 squared. Now look, 12 to the 8th times 5 squared is some number, right? We're not spending time evaluating that right now. We're not actually coming up with what that whole number thing is. That's not the goal of what we're doing here. Yeah, I think at some point, really, I'm literally just writing out an answer key for you at this point. We are going to pull this will be a u cubed. And because we're subtracting the two logs with the same base, we'll go ahead and divide these v to the 18th power. Now, I don't think they're going to plan on tricking you. I haven't looked hard enough yet, but don't just assume that you can automatically subtraction of logs is division. You got to make sure they're the same base. You got to make sure they're the same base, and they are for these. And I don't think they're going to change bases on you here. Excuse me. Okay, here we go. Number 25. Now, this might be a little better for me to keep these separated for a moment to talk about the new little bit here, where we now have here's z squared plus. Think of this as a 1/2, right? Dividing by 2 is multiplying by 1/2. So that's log base 5 of x. So now that 1/2 is going to go up into there. So that's log base 5 of z squared times, and I'll put the times part here as well, x to the 1/2. And you would be done, but as you saw that we came from what appeared as radicals before to us converting to that fraction exponent, to pulling it out in front and making it division, let's convert this, into a radical. It's been a long day, guys. It's been a long day. It's past 10 p.m. here, and I woke up at 6 something. So z squared times the square root of x right there to the 1/2 power is also square root. So there's just that last little bit that'll turn it into something that we've seen on the previous page. What I'm really doing is making things here match what we see on that page, what you see on that page, and making things that we see here match what we saw on that page. So when we saw things like the cube root of and things like that, that's kind of the equivalent of what I'm trying to do here for these ones. I hope that kind of makes sense. And we'll continue on that. Okay, nothing new for this one. Same base, and its subtraction of the logs is going to become a division. So this will become, So as long as nothing's new, I'm going to kind of try and go in one step as often as I can, as often as it seems to make sense to. And this is, in fact, one of them. Dividing those, bringing those exponents up. And number 27, more of the same thing. For a lot of these, until we get maybe to number 31, apologies on that, because we just have so much more to cover. Now, this doesn't have a base here. I just want to mention it doesn't have a base. But it doesn't have a base mean they're the same base. It means it's base 10. So 8 to the 6th over 11 to the 30th. Log base 10 of those two. You don't have to write the 10. Just know that without it written, it's the same base because they are both 10. You will have to know that later. Okay. 11 to the 4th. 7 to the 4th. Divide them with log base 9. 11 to the 4th. 7 to the 4th. If I keep yawning, I'm going to have to do something about that later, because I cannot have that on a video. This needs to be professional, guys. It needs to be professional. I don't know, at some point. Oh, another log with just base 10. Huh? So log of x cubed over y to the fifth. I think for the first time, I'm bored with math when I feel like I'm not actually teaching something. Right now I'm talking over just problems, you know what I mean? They're not problems, they're all solutions. So I get bored over not being able to teach you anything new. Right now I'm just going like, how do I pass the time? I can't even tell a joke. All right, so here's more of the same that we saw from before with dividing by 2, but now we're dividing by 3. Dividing by 3 is multiplying by 1/3. Multiplying by 1/3 is inside a log, raising to the 1/3. So, as this is a product, we can probably get to this stage pretty handily here. I'm sure you're accepting of the fact why these are written the way that they are right here, with that sum of the logs represented as a product inside all the logs. But what I can do is make these both cube roots, cube root of x times cube root of y. But as they're both cube roots, let's put them under the same cube root hat together. So this can be written as the natural log of z times the cube root of x, y, like that. And that'll be your result there. So cool, something new. Now it's not z cubed, that's z times the cube root of. Okay, so back to some other stuff here. Same base, so log base 4 of x cubed times y. You can see I was excited about something, and now I'm like, oh man, back to this stuff. All right, here we go. 4 more problems with the condensing thing. We're almost done. You see I got to write less, though, and that's good. So subtraction of the logs is division inside a single log. It's both the same base. So log base 4 of a to the 5th over. You know what I might do? You know what I wonder? Hold on. It's not for this problem. I was going to say, you know what kind of problem we haven't seen, but I just realized why we haven't. We haven't seen one where they were being raised to some other powers. And now that I'm thinking about it, I do wonder, when we look at a problem like even this one right here, let's take a look at this one up here. I wonder if it's better to write that, if the best answer they'd show me, and I'll put the brackets in, is 11 over 7 all to the 4th power, right? That would be kind of a bigger answer that. So whatever greatest common factors of these numbers, this one, log of, see, I'm intrigued by this one, 8 over 11 to the 5th all to the 6th power. Whoops, that needs to be a square bracket. But you know what I mean? I wonder if that is probably the better version of what we should be writing on some of these because of its nature. All of these ones that have that. The first one even. I'm not going to do it for all of them. It seems like it's doing it too much. But you know what I mean? I'm saying that because these ones had those all over the place as well. So they broke it to their basic essence there. I don't know. I'd have to really check a key on that and see if they're like, yeah, we're going that deep into it. I don't think so, though. Okay, now these divided by 2s means those are both times 1/2, erase the 1/2 power inside the log. So those are going to be square roots. Let's see if we can do this all in one step here. So this will be log base 9 of z times the square root of x times y. So again, that's because these are dividing by 2 is times 1/2. Times 1/2 is raised to the 1/2 power, and the 1/2 power is square root of, and both of them are inside the same square root. Okay, 2 more. So with this one here, log base 2 of 11 to the 4th, that minus will be division here, minus the log base 2, 6 to the 6th power. And again, I feel like I can pull some other things out there, but just the practice. And last one, we know that dividing by 3 here will ultimately mean the cube root. Looks very similar to this problem here, only it's a natural log base 7 instead of a natural log. So here this will be log base 7 of z. I mean, it's even a product still, times the cube root of x. Why? Don't make me bored of doing math. It's just whenever I can't teach it. This is supposed to be brand new and exciting. Okay, the next set of problems here, and again, there's a lot of blanks left over. There were things written here, all those problems. We ain't doing those, so I'm covering all those up. Hope you don't mind. Covering up a bunch of problems so we can solve. Okay, The essence is now to actually solve for variables in these equations. Now, they are missing parentheses. I really wish they had them. We are going to solve for v in this. For what value of v would make this statement true? Your ultimate thing to do here is to get the log term, the log portion by itself on its own side of the equation, and you can use any sort of conversion principles that you have, such as the log. I want this to be tired. If the log base b of x equals y, then b to the y power equals x. This exponential conversion is something that's an equivalent of what's there. And you can only kind of get it to that stage if you do have this log represented. Now, I could take this -9 and put it up in this exponent right here, but I'm not going to play with it that way. It's easier to get this log part by itself. So if I divide both sides by -9 like this, because of course the -9 is multiplying out in front, this will become log base 11 of 2v equals 2. Now, this does come into this conversion right here, and I'll give another reason as to why in just a moment, but first let's just go ahead and write that out. That means that 11 to the second power, 11 squared, equals 2v. Okay. Now, another way to consider this is by knowing this part. Exponents and logs are inverses of each other. If you raise some base to log of that same base with some value, we get to ground the thing that's inside the log here, and we get to cancel that part out. I canceled out exponent base with log of same base of that thing, and it just leaves me with x. The point of this is, if I treat these two things as x, well, actually, let me write one more thing, one more property. If you have two equal bases, let me try that again. If you have two equal bases with some exponents, you can set those exponents equal to each other. I'm sorry. You can set those bases equal to each other. What also works the other way. If you have two things equal to each other, you can raise them as exponents with equal bases. If I raise these as 11 to the, let me do it in black, 11 to the log base 11 of 2v and 11 squared like that, it's kind of a magic step if you will, doing that right there. What happens is this part kind of cancels and you're just left with 2v, and that'll equal 11 squared. Well, guess what? 2v equals 11 squared. And I mention that because I will be doing the same thing on the other version of it when we have exponents, and I'll be logging both sides instead of converting it to its log form. I kind of want to give you this notion of this is how these things work. You do need to know this property. You need to know how these are inverses of each other and how that actually makes sense in its own right. Anyway, we're not done in solving for v here. 11 squared is 121. And then you divide both sides by 2, and you get v equals 121 all over 2. 60 and a half, 60.5. All right, so a lot of these will kind of have that same stuff going for them. So let's check out even more. -5 plus log base 7 of negative x equals 3. And go ahead and add 5 to both sides, and you'll get log base 7 of negative x equals 2. Now, they say you can't take the log of a negative, but we're asking for what values of x make this true. Remember, x can be negative numbers. X can be. So the opposite of a negative is a positive. So there are answers to this, such as when you do 7 to the second power, you'll get negative x. Or 49 is negative x. Or positive x is negative 49. This is the value that you would take to get that. And that's it. All right, 127. Now you notice no parentheses around here, but does that mean that I just wrap parentheses around this part automatically? No. You can even see right below it in problem 133. Notice how they do put parentheses. They put parentheses around things when it's more than one term, when they're quantifying something. So if they're not quantifying multiple terms here, that means the implied parentheses are actually just right here. The -8 is not inside the log. The -8 I'm going to be getting rid of on this side by adding 8 to both sides right now as I isolate my log term. So this will be log base 6 of negative 3p equals 2 negative 6 plus 8. If you see my magic step version, not magic step, but if you see the step, actually the other way is the magic step converting. If I do this magically, you'll get negative 3p equals 6 squared, or 36. Right, because the cancellation here. Boom. Divide both sides by negative 3, and you get p equals negative 12. That's it. All right. 128. Log of k minus 3 minus 7 equals negative 9. So we are going to add 7 to both sides. We get log of k minus 3 equals negative 2. Now, two things of this to note. Actually, one thing of this to note is that this is log base 10. Right? If you can't see the thing, then it's log base 10. So, kind of in that vein, again, it's 10 to the negative second power equals k minus 3. All right. The second thing to note that I was going to mention here is that this, this 10 to the negative second power, that's 1 over 10 squared. This is 1 over 100. K minus 3 is 1 over 100. Now, if you, I don't know how often I'm going to answer in this way here, but we got to get, we're going to get an improper fraction here, right? K equals 3 plus 1 over 100. How about we put 300 over 100 to get 301 over 100? The point I was going to make was I'm going to try and refrain from calculator use, and I'm going to put these as improper fractions because these will happen sometimes, right? We're going to get those k values that way. It's just a little more than 3 as an answer, right? 3 and 1/100ths, 3.01. And that's the answer to that one. Okay, number 133, and expect possibly some more of those coming up. So divide both sides by negative 9 here. You'll get log base 6 of r minus 7 equals negative 2. 6 to the negative second power equals r minus 7. If you add 7 to both sides, r will equal 1 over 36 plus 7. Mr. Robinson, where did you just write all that stuff from? That looks way different from here to here. Well, 6 to the negative second is 1 over 6 squared, which is 1 over 36. I flip-flopped these to put the r on this side because I like to do that, and I added 7 to both sides. So 1 over 36 plus 7. Now, if I want a common denominator, I'll have to multiply top and bottom by 36. This is the part that isn't as fun with me. 7 times 36 is 252, I think. Plus 1 is 253. That was kind of harder to do. 253 over 36 should be that answer for R. All right, number 34, divide both sides by 5 here. We'll get log base 6 of b minus 9 equals 4. Well, let's put a big old 6 on both of those right there. Cancel that part out. Yeah, b minus 9 equals, 6 to the 4th. I think 1296. I hope I'm right. 1296. Add 9 to both sides. You get b equals 1305. It's a big number that's going to make that happen because it's 6 to what power gets us, 1296. It's just 4. So yeah, that's gonna do that. In fact, is there a way I can try and do some of these in my head? Negative 7 times something is 7, right? Negative 7 times negative 1 is 7. 6 to what power gives me negative 1? I don't know. I don't know. I guess I'm not going to do it that way. Okay. I'm sorry. It's not 6 to what power gives me negative 1. 6 to the negative first power is what? Okay, that's why. Okay. Let's go. Divide both sides by negative 7. We get log, I've used green too much here. I'm very tired. Log base 6 of a plus 8 equals negative 1. I was going to say 6 to no power gives me negative 1. I was going to say, but this answer's possible. 6 to the negative first power equals a plus 8. 6 to the negative first is 1/6. So a is 1/6 minus 8. Now 8 times 6 over 6 is 48 over 6. So that'll be negative 47 over 6. That is the a value that makes that so. Geez, I never would have found that out in my head. A lot of 9s on this one. Number 140. Divide both sides by 9 though. Log base 8. Are all these negatives the rest of the way pretty much? I'm not looking forward to that. Log base 8 of n. Hey, this is what I gave my students. Log base 8 of n minus 9 is negative 1. They hate me now. 8 to the negative first power. They're saying you do these problems. That's kind of why I'm doing them. They're like, so Robinson, this is a lot. And I said, it's not a lot. And they said, can you make a video? And I'm like, no, it's a lot. So n is 1/8 plus 9. 8 to the negative first is 1/8. Adding 9 to both sides is plus 9. 9 times 8 over 8 will give me 72 over 8. So this is going to be 73 over 8 right there. All right, let's keep going. Number 145. Subtract 1 from both sides. You'll get negative 6 times log of 6x minus 7 equals 12. Divide both sides by negative 6. You'll get log of 6x minus 7 equals negative 2. Now, this is a 10 that's going on right there. So if I, work my 10 magic, then it will cancel this part out, leave me with 6x minus 7. So 6x minus 7 equals 10 to the negative second power. That's 1 over 100. So 6x minus, got to add 7 to both sides. So 6x equals 1 over 100 plus 7, which is 701. I'll just put 6x, because 700 over 100. That's 701 over 100. Now, if you divide both sides by 6 here, that's the same as multiplying by 1/6. I put that because it's easier to do 100 times 6 instead of, you know what I mean? So we're going to get x equals 701 over 600. There's an exact value for you right there. Okay, here we go. 146. Subtract 5 from both sides to start with. 8 times log base 6 of 2x minus 7 equals negative 16. Divide both sides by 8. We get log base 6 of 2x minus 7 equals negative 2. Again with the negatives. So 6 to the negative second power equals 2x minus 7. If I add 7 to both sides here, and that's 1 over 36, right? 1 over 36 plus 7. I think we've seen that number, right? Was it 252 or whatever? Yeah, 1 over 36 plus 7. So that same thing. So 2x equals 253 over 36. If I divide both sides by 2, that's the same as multiplying by 1/2. So right there, and I doubt that'll be any more reducible later. So x is going to be 253 over 72. I hope I'm doing that right. I'm not using a calculator right now. All right, last two on this side before who knows what's happening on the other side here. 10 times log base 12 of 7 minus 3n minus 4 equals negative 14. I'm going to start by adding that 4 to both sides right here. If all of these are negatives, man, that's unfortunate. I didn't realize they'd just be negative after negative here the rest of the way. No wonder all those are fractions. 7 minus 3n equals negative 10. Divide both sides by 10. You get log base 12 of 7 minus 3n. I'm sure all my students just use a calculator. Equals negative 1. So 12 to the negative first power equals 7 minus 3n. This time, I'm going to add the 3n over, make that positive. I want to make that positive before negative. I'm going to put the 12 to the negative first over by subtracting it, and that's 1/12. 7 is 84/12. So 84/12 minus 1/12 is 83/12. Divide both sides by 3 is multiplying by 1/3. And we will get n as 83 over 36. I do believe. And last one right here. This one looks a little more fun because it looks like I'm about to add 6 to both sides right now, and that'll give me 0. So negative 7 times log base 9 of negative 4b minus 9 equals 0. Divide by negative 7. Log base 9 of negative 4b minus 9 still equals 0. I mean, ultimately, we are asking this to be 1 because the log of 1 is going to give you 0. But if I'm just going to write this out, 9 to the 0 power equals negative 4b minus 9. So that 9 to the 0 is 1. So we need negative 4b minus 9 to equal 1. And of course, I'm going to make my b term positive. I'm going to add this over. 4b equals negative 1 minus 9. So b is negative 10/4 or negative 5/2 right there. I believe that's it. That's the b value that works out. Okay, now let's see what's on this other page here. Oh man, 2 more problems of that accord before we do these. I'm sorry about that. And then we'll get to some of these here. Okay, let me check something here really fast. Okay, never mind. All right. Here we go. Subtract 2 from both sides. Negative 2 times log base 11. I mean, these aren't as mundane as the expanding and condensing ones because those were all the exact same problem, literally. Log base 11 of 10 minus 6x equals, divide both sides by negative 2 is negative 2. So 11 to the negative second power. Let's see how much you guys know about this stuff. I'll do the 11 this way here. So that cancels out that and gives me 10 minus 6x. And this is 1 over 121. I'll keep the x negative this time. Negative 6x equals 1 over 121 minus 10. You multiply that by 121. That's 1210. 1210 over 121. So that's negative 6x. See, I don't like negatives. Is negative 1209. Oh, gee, I don't know. And divide both sides by negative 6 is multiplying by negative 16. It'll make this answer positive, and it's going to make the bottom 6 times larger. So I believe it's this. X is 1209 divided by 726. Ooh, I wish I had a key in front of me there, but I believe that's the answer. All right, and lastly, on 156 here, subtract 8. Oh, it's going to be a positive. Good. I missed those. Subtract 8. Divide both sides by 3. Man, when did we get this problem earlier? It's good to finish on something like this. So 7 to the first power is 7a minus 2. 7 first power is 7. Add 2 to both sides. And divide both sides by 7. You get 9 sevenths for a. I'm happy to have a fraction on there. Provided everything else that happened. Okay. Solve each equation, round your answers to the nearest 10,000th. That's 4 decimal places. If you're okay with it, I'm probably just going to write 3 on most of these here. I'll show you the calculator on some of them to make sure we do it. Now, in order to do these problems most efficiently, you want to condense the logs. You want a single log on both sides of the equation. You want to isolate your logarithms down to, you don't want them in multiple terms if possible. So you want to condense them. And then you want to use kind of that property that we were talking about, or kind of something equivalent. If the logs of the same base are equal to each other with stuff inside, you set those things equal to each other. And on that note, make sure the answer you get for a log is not a negative number, because we cannot take the log of a negative. That'll be a domain restriction. That's what I was checking on to see if these were just log of x each time, and it looks like they are. So bottom line, or 0. If the thing you're taking the log of is 0 or negative, it is extraneous. It doesn't work. And that's unlikely to happen on these unless they set it up in such a way that they were just testing you. But if we had quadratic equations or something like that, yeah, it's possible to have happen. Okay. So right here, this subtraction means, this is the condensing part, we are going to go ahead and divide those as a single log like that. Now, the idea is we're taking the log with the same base, right? They're both base 10. Taking the log of the same base right here, setting them equal to each other. How is it possible to make these logs equal to each other without just making these parts equal to each other right here, right? If log of x over 6 equals log of 20, then x over 6 has to equal 20. Otherwise, they won't equal each other. That little thing is you could say, hey, 10 to this power, 10 to this power, and they cancel out, whatever. Then you're left with x over 6 equals 20. Multiply both sides by 6, you get x equals 120, which is clearly a positive number. So as long as it's positive, you're good. Look, it's not like this. It's not like the answer is 26. It's not log of 26 minus log of 26 is log of 20. It doesn't work like that, right? That's why you can't cancel things early. Okay, so right here, this becomes a product. This is log of 6x equals log of 53. We did so much condensing before that I believe that you can understand what's happening there. So we can set 6x equal to 53. Divide both sides by 6. We get x equals 53 over 6. They do say round your answers nearest 10,000th. If it's an exact number, I'm not going to bother with that. I'm going to do it if I have to take the log of something. And there are, I'm sure, where we are going to have to do that or have an exponent kind of answer. So if we do, I'll be happy to do that. Otherwise, fractions are fine for me. This is log of 4x. And again, this is based, all these are base 10. And that's why, it doesn't matter what the base is. The point is they have to be the same base on both sides for these kinds of problems. So this will be log of 4x equals log of 38. As long as they're logs, they have to be the same base. Otherwise, the problems aren't as fun. There are things you could do. It's just not as fun to do. So 4x equals 38. Divide both sides by 4. You get x equals 38 over 4, which is 19 over 2. Okay. This is log, again, not much to say on these. Log of x over 4 equals 1. Oh, this isn't a log. This is just equals 1. So this is the part, now we're convert to exponential form, whatever else. So this is, you raise 10 to both those powers, both his powers there, kind of like that. And you get x over 4 equals 10 or x equals 40. And if you're not comfortable with that, you could just 10 to the first is x over 4. That's fine. So x is 40 there. Okay, looks like these missed the log. These next couple missed the log things until the last one there. So just be careful. You're not making up logs where they aren't. I didn't even catch wind of that. So this is log of 8x equals 1 again. And again, that's a 10. If you want to do your conversion version, that's 10 to the first power is 8x. So 8x equals 10. Or x equals 10/8, which is 5/4. Again, no reason to really round there. Log of 5x equals 2. So remember, it's 10 again. So I guess it is important to know these are 10. So that's 10 squared. So 10 squared is 5x. 5x is 100. Divide both sides by 5, you get x equals 20. All right, drill and kill. Here we go. 179 log of 8x equals 3. That's 10 cubed that equals 8x, 10 to the third power. So 8x is 1,000. Divide both sides there. I think that's 125. Divide both sides by 8. And then lastly on this page here, we have log of x over 4 as we condense that equals log of 3. So this is back to just, 10 to both those powers. X over 4 is 3, so x is 12. Let's just make sure none of these had negative or 0 x values. They did not, so you're good. Nothing's, not extraneous, but nothing's a no solution case there. Okay, the last page here, the last 2 pages, now these are ones that I made. Or at least, I set up and stuff. So there's kind of growth that occurs here. It does say round to the nearest 10,000. This is one where I might be rounding in 3 decimal places. This is where we are going to have to use the calculator almost exclusively, like all the time. And I probably won't even show it each time. In fact, here's my individual personal calculator. I'm probably going to be using this every so often afterward to just say, type it in, see what you get. But I got to show you some other things alongside that. Okay, some properties that will be used here. That are new. Well, I'm going to revisit one. We're going to revisit this property here. Log base b of x to the a power equals a times log base b of x. I'm going to say that right now it's not going to be in use right now. I do want to mention that the log of 10 is 1 and the natural log of e is 1. The idea of this is as we log both sides of something with those bases, with base e or base 10, it'll essentially cancel out that thing. So whenever I say we log both sides with a base of 10, that's why it'll go away. And what was the other one? Well, here's something else we're going to use. Log base b. Oh, I remember. But log base b of b to the x is just x. See, what happens is that x. I don't know. I don't want to over-explain it, but kind of look at this property, and log base b. I don't know. I know, but I'm going to be over speaking here. Log base b of b is also 1. Right, because this log of 10 is the log base 10 of 10. Natural log of e is log base e of e. Log base b of b is 1. That's kind of the worst. But the last one I want to mention here is going to be a change of base formula 1, but I'm not going to be using it too much. Log base a of b is log of b over log of a. Or you can natural log of b over natural log of a. The idea is something you can use in your calculator. Something you can use in your calculator. And we have a log button in our calculator and a natural log button in our calculator. But your calculator likely doesn't have a change of base button because our calculators work in base 10. Okay, so here's what we're going to do. We are going to solve for the variable. This is where logs are king. This is why logs exist. They're inverses of exponents. You have a variable in your exponent. Let's ground it with logs. So 10 to the p is 63. What value of p can you raise 10 to get 63? We know 10 to the first is 10. We know 10 squared is 100. Our answer is somewhere between 1 and 2. What is it? We'll log it out. First, I'm going to rewrite this thing to give myself some room to actually write that version of it. And I know that a lot of you guys will just write your conversion of log stuff, but I'm going to get used to this idea for some practical reasons. I think it's more helpful to do it. So I'm going to log both sides of this equation like this. I'm going to log and log. This allows me to kind of use some of the properties and principles that are here. What's going to happen is log of 10 is 1. The p comes out, multiplies in front. P times 1 is p. The log base 10 of p to the, the log base 10 of 10 to the p power is just p. It's just p. So this gives me p over here, and this becomes the log of 63. Now log of 63 is an exact answer. The approximated answer is something that I am going to go ahead and round because the whole goal is to get to something of value for us. Oh, I'm going to use the calculator on my screen. Sorry about that. Maybe not for all of them, but I will for some of them for sure. So let's go to this one. This will be log of 63. So I got my log button right here, and then 63 like that. And that's going to be that number, 1.799. I'm just going to go ahead and use 3 decimal places there, 1.799. So that is what it approximately equals. That's what 10 to that power gives me 63. So yes, I will be rounding these ones, as long as it's not some exact something. Or no solution. Okay, so e to the x is 88. So I'm going to rewrite that. E to the x is 88. Again, give myself some room because I'm going to log both sides. But specifically, on these first 10 problems, they're all either base 10 or base e. Saying logging both sides means log base 10. Natural logging both sides is log base e. If I do that, that'll outright cancel my 10 or my e. So I do want to not just log both sides, I want to natural log both sides because that'll ultimately rid the e completely. Natural log of e is 1. Log base e of e to the x is x. I will just be left with an x here. And here I have natural log of 88, which will be my exact answer. And my approximated answer here for natural log of 88 is, here's my ln, 4.477. 4.477. So again, I'm doing 3 decimal places instead of 4 for these ones here. There you have it. All right, number 3. Before I, just like the log things before, we had to isolate the log on one side of the equation, just boom, work that out. So we have to isolate this 10 to the v power before we use log things. I can't just log right here and have all be good because log of a sum doesn't get me anywhere as far as canceling the 10 out and things like that. That's not going to work the way I want it to unless I subtract and combine it with other things here. So if I subtract right here, I get 10, oops, let me give myself some room. 10 to the v power equals 93. And now I will go ahead and log both sides of this thing. Of course, base 10. So that'll leave me with v on this side and a log of 93 on this side. And of course, log of 93. I think this is where I'm going to, unless there's something different I have to change to, this is where I'm going to use my other calculator, where I'm getting about 1.968. Okay. Number 4, there's something multiplied in front of my e to the r power. We're trying to solve for r, and there's the e is not a variable, it's a constant. But negative 4 is multiplying in front. So if we divide both sides by negative 4 before we proceed forward, we'll get e to the r, the 4 before we proceed forward, is positive 25. And it's good that it's positive because if it was negative, then there would be no solution as we natural log both sides because you can't take the natural log of a negative. Natural log of e to the r is just r. And that's the natural log of 25, which is approximately 3.219. 3.219. How much time have we gone so far? Oh, over an hour. That's a long time. All right, number 5. Adding 4 to both sides to start with here will leave us with 10 to the p minus 3 equal to 79. I will log both sides. Of course, logging is base 10, and it will ground the entire p minus 3. Really briefly, before we actually just do outright canceling, let me show you the idea of what happens when you ground that thing. P minus 3 goes out in front. It is p minus 3 quantified times log of 10, right? That's how that part works. The whole thing multiplies by whatever that is. Now, thankfully, right here, log of 10 is just 1, right? If you type log of 10 in your calculator, just get 1. So you're just left with p minus 3. I mean, the p minus 3 is all that's left. I just want to make sure you know it's the entire thing that's multiplying. So we add 3 to both sides, and you'll get p equals exactly log of 79 plus 3. Now, the plus 3 is outside of that log. And, of course, if you see an answer key, that answer key will say log of 79 plus 3, and people will turn that into log of 82, or they'll type in their calculator log of 79 plus 3 and not close the parentheses. You can tell why I'm very, very, very stingent upon using parentheses around wrapping your log function. I think it's important there. So log of 79, close parentheses, plus 3 is 4.89, round up 8. I'll show you on the calculator this time. I'll go ahead and type both of them in and kind of give you that idea of, what's the difference between log of 79 plus 3. Remember, this says 10 to what power is 79, and then add 3 to it. So that's the correct answer. This one is saying, this one is saying 10 to what power is 82. If I did 79 plus 3 like that, and I just let it go. 10 to what power is 82? Well, that's a way different answer, right? 10 to the 1.9 power. The first one is what we want with this thing, So, not a fan of them not closing parentheses when they don't. That being said, let's keep going. Add 9 to both sides, so e to the 10x equals 25. We shall natural log both sides here. Cancels out the e stuff, grounds the 10x. We're left with 10x equals natural log of 25. Divide both sides by 10 before you evaluate these things, please. First get the kind of exact answer first, and then we go ahead and use the calculator. So now we go and use the calculator there, and that's natural log of 25. And again, the divided by 10 is not inside the natural log portion. It's outside of it. So that's approximately 0.322. 0.322. It rounds up. Try it for yourself. All right, number 7, there's a negative 4 multiplied and a minus 1 here. So I'm going to add the 1 first. We get negative 4 times 10 to the negative. Please don't multiply those together. The order of operations got to do this first. Equals negative 40 if you add 1. Then divide by negative 4, you get 10 to the negative 10x equals positive 10. Ooh, hold on. Move that. So let's go ahead and log both sides there. Now, the log of 10 is 1, and I'm mentioning it over here, but even on this side as well. I don't need to use my calculator for that. The log of 10 is 1. This, I'm just left with negative 10x. So negative 10x is 1. Divide both sides by negative 10. Excuse me, you get x is negative 1/10. All right. Here we go. Add 9 to both sides. Negative 6 times e to the x plus 1 is negative 31. Divide both sides by negative 6. You get e to the x plus 1 equals positive 31 over 6. Now, that's a fraction involved. That's not a terrible thing. You're just going to type that in your calculator. Just make sure it's all inside the natural log when you calculate it. Don't worry about what decimal is it. It's reduced a fraction. Don't worry about that. Your new natural log is going to be a weird number anyway, right? So all cancels out but the x plus 1. You get x plus 1 is natural log of 31 over 6. So x plus 1 happens to equal x happens, that's the same thing. X happens to equal natural log of 31 over 6 minus 1. I'm sorry if it seems like I'm rushing. And you're like, wait, I'm trying to write, I'm trying to listen, I'm trying to whatever. This has run its course. I promised my students I'd do it, and I'm doing it. All right, 0.642. 0.642. There you go. There you go. Enjoy that one. All right. Number Not, and don't worry, I'm not bitter about it. I'm just saying, let me do me as a result of this. I'll go fast if I want to. Especially when it's just algebra, right? Nothing really is changing so far. Add 6 to both sides here. We get negative 6 times 10 to the negative 3r minus 6 is negative 42. Divide by negative 6. Negative 10 to the negative 3r minus 6 equals positive 7. So when I, didn't write much room, but that's okay. When I log both sides, like that, that's going to give me negative 3r minus 6 equals log of 7. And we still got 2 more steps to go before we kind of write out an answer. Again, please don't round that part early. Don't round this early. Because you'll have rounding errors with it. Add 6 to both sides. And divide both sides by negative 3. We'll get log of 7 plus 6 over negative 3. There are better ways to write that answer because you shouldn't be a negative inside the denominator. But since we're rounding anyway, it's totally fine. Just make sure you do this correctly. So I'm going to go to the calculator for this one. Make sure that you type it correctly here. There's more than one way to do these. I know that some calculators even have a fraction button. Say that it didn't. Say that you forgot about it. Say that you were in a mode that could do it. You have to, and say you did this in one calculation. You should wrap the numerator around parentheses. Log of 7 plus 6. Close the parentheses. Divide it by negative 3, like that. Or put the negative in front of the parentheses to begin with, whatever. But this is the correct answer. You can't type log of 7 plus 6. Like, check this out. You can't do log of 7 plus 6 divided by negative 3 like that. That's going to be a different answer. This is not the correct answer right here. It's going to be this one. Because this just divides 6. This becomes log of 7 minus 2. Because only 6 is dividing by negative 3 here. This is the whole top divided by negative 3. Some people safely just calculate the top, press enter, divide by negative, press enter, things like that. So it's going to be negative 2.282 rounded. I didn't type that correctly. There we go. Okay. Number 10. Negative e raised to the negative 8n minus 7 plus 10 equals negative 63. Ooh, a lot of negatives. All right, here we go. That's negative e to the negative 8n minus 7. If I subtract 10, we get negative 73. Now, there's a negative in front of this e, blah, 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 blah. A lot of people think this is a negative e that's happening. No, it's not e that's negative. It's e to the negative 8n minus 7 that's negative. This is the same thing as doing negative 1 times e. Remember when we did negative 6 times e and 10 and things like that? We divided by it. Let's divide everything by negative 1. Let's change the signs. E to the negative 8n minus 7 equals positive 73. Unless this was around parentheses, which it wasn't, you have to treat it like so. Now we can natural log both sides. And now we'll have negative 8n minus 7 equals natural log of 73. So you can see the problem is going to be a lot like the previous one where you got to make sure you group things correctly. I'm not going to need to show that in the calculator necessarily if you were good on number, I think, 9. So I hope you're good there. So natural log of 73 plus 7 all divided by negative 8. Let's see what we get here. Natural log of 73 plus 7 divided by negative 8. So we're going to get negative, if I typed everything correctly, it's negative 1.411. Right there. Okay, now that is it for the log bases of 10 and e. Now we're going to be working off logs that are of different bases. And the difference here when we do that is quite substantial because you can't automatically cancel something out unless you use that base. So if we look at the first one here, 16 to the p power equals 77. The way I could cancel out the 16 is if I logged both sides with 16 as a base. And that's all good and great. That's something that you can do, and it's fair. Log base b of b to the x equals x. This would be left with p on this side and log base 16 of 77 on this side. The problem is our calculators cannot change the base for log. When it's just you type log, it's just log of 10. Fortunately, there is a property that allows us to do it, and that was what I wrote up here earlier. Now, this is not the way I'll be doing these problems. I'm just showing you the property for what it is. It's right here. The log base a of b is log of b over log of a, or natural log of b over natural log of a. As long as you use the same base of log base 10 or log base e, then you'll get the same proper answer. So you could, and this is probably what a lot of people are going to start doing as long as you know how to do it. If you don't, I'm going to show you an alternative method that shows why this property is what it is in the first place. But this is what you can type in the calculator. Or this is what you can type in the calculator. And either way, you'll be getting the same value. 16 to what power is 77? More than 1 point something. 1.2, I don't know. We're going to figure it out though. We're going to go ahead and calculate it. So I'll go to the calculator and I'll show you a log of 77. Oh, must have hit the second button before. Log of 77 over log of 16. 1 point, oh, not close to 1.2. 1.566 or 1.567. If I did natural log, you'd get the same thing. Natural log of 77 over natural log of 16. And same answer, right? So, okay, cool. So that's the answer. Now, I'll show you the second way of doing this problem right after that. So 1.567, if you go. Okay, so there's one way to do the problem. Now, alternatively, here's what you can do. You have, we'll figure out the room after. You'll have 16 to the p power equals 77. We will just log both sides. We could just natural log both sides as well, but for the sake of this, I'm just going to log both sides. We'll log both sides. Now, the property that we know, this is log base 10, right? So nothing's going to cancel here. But the property that we know is that this exponent can go out in front and multiply by this thing. P times log of 16 equals log of 77. If I want to solve for p that's multiplying by log of 16, I'm going to have to divide both sides by log of 16. Like that. You know what p equals? Look familiar? P equals that. And this is the more conventional way of doing it. This kind of shows why this property exists for what it is. I know that we can mesh that property as we see fit. I don't have a problem with either or, but I think you're going to see this more often from me. Sometimes you'll see me write natural log, I guess, just because I tend to just write log. When I say you log both sides and it grounds the p, etc., that you know that that's what's going on there. But of course, you do log base 16. You'd have to know that property for what it is, but I think it's better for you to know why it is. And I'm sure there are times, I can't remember now, but I'm sure there are times where it's almost a must to do this instead of this kind of thing right here. Okay, so we're going to go on and move on to number 12 here, and I'm going to be doing that same stuff. I have 9 to the n power equals 32. So I'm going to go ahead and log both sides. I guess right here I'll just say natural log. I'm going to natural log both sides here, and that'll leave us with n times natural log of 9 equals natural log of 32. So to solve for n, we will take the natural log, or we'll divide both sides by natural log of 9, and do natural log of 32 over natural log of 9, which of course is the same as log of 32 over log of 9. If you don't believe me, try it for yourself. But natural log of 32 over natural log of 9 gives me 1.577. 1.577. So you'll see a lot more of these kinds of problems here. They will grow just like they grew in the previous problems. We got to get the exponent thing by itself first, and then we log both sides and do that. It's a lot of drill and kill for my students, but I hope they really get it after all this. Add 2 to both sides here. You get 16 to the n power is 29. So I'm going to go ahead and log both sides there. Oh, something just popped up on my screen. It reminded me when I'm waking up. I don't know, when I set a waking date for something, or a waking time for something. Hold on. There we go. Okay. So that's n times the log of 16 equals log of 29. When you divide both sides by log of 16, we get n is log of 29 over log of 16. Don't think this is the only video I've recorded this evening either, by the way, which is sorry, 1.2 2, 1, 4. Give me 1 second. I'm going to go back. Wait, hold on. Never mind, we're good. I did a problem with my students before, and I was thinking which problem was. It must be a later problem. I was thinking of something on the first page. I'm like, I don't remember running into the problem yet, but I guess we'll get into it soon. Never mind, you're good. All right. All right, there we go. I'm just going to move forward. Right now, I'm just doing the problems. Divide both sides by 4. 11 to the b power is 10. Now, listen, I'm going to log both sides. And log of 10 is that's 1. I don't even need to work off that part. I do need to work off log of 11. B times log of 11 is 1, right? So now b is 1 over log of 11. It's kind of interesting to think about it that way. By the way, let me just mention this because we're seeing this each time, right? Log of b over log of a, right? We know it's the change of basis thing, but it's not log of b minus a, right? There's only one direction that log thing works. You can do log of b over a to be log of b minus log of a. Log of b over log of a isn't log of b minus a, right? It doesn't work that way. So I was going to say, don't turn this into log of 10 minus 11, So anyway, I just wanted to say that. So 1 over log of 11. By the way, here I can't type natural log of 11 because it's not the same log on top and bottom. If I kept it as log of 10, I could have done natural log of 10 over natural log of 11. That would have been fine. But once I turn this into a 1, I'm assuming base 10. I must use log of 11. Natural log of 11 would have been a different number. So this is about 0.960. I notice I'm using a lot more black here. Once I rewrite my problem and I log both sides, I end up just using black. All right, 14 to the 2x power equals 58. Let's go ahead and log both sides there. So we're going to do some more work after the log portion of this, and this is where things can get a little trickier. I think this is what I wanted to mention here. So this is 2x times log of 14. It's not necessarily trickier, but you got to be careful on how you write your answer. Equals log of 58. Whoa. Log of 58. And I'm not just dividing both sides by log of 14. I'm also dividing both sides by 2, right? Divide both sides by 2 times log of 14. I want to get x by itself. You could do it in 2 steps, but I don't need to. So right here, I'm going to type that out to kind of figure out what x is and approximate it. Now I'm going to go to my calculator again, where you have to be careful of the whole order of operations thing. 2 is multiplying by log of 14. They're multiplying together in the denominator. They're both being divided. But if I go to my calculator, I'm going to type something wrong first. So what I don't want to do is type log of 58 divided by 2 log 14. This will not be the correct answer. You won't know one way or the other just by going, well, I trust it, right? In fact, I would trust that answer too. If you just said, Mr. Robinson, is this right? And you hid the rest of it. Sure. Your calculator. How can your calculator lie? The problem is log of 14 is not multiplying by 2. It's multiplying by log of 58 over 2. This calculator is taking log of 58, dividing it by 2, and then it's multiplying it by log of 14. And it's getting that number right there. What we want to do is divide by log of 14. We want it in the denominator. So you have to make sure that you are dividing by that quantity 2 times log of 14. Like that. And this is our answer, 0.769. You're like, the other answer looks better. It did look better. But this is 0.769. So that's the correct answer to that one right there. And that's the difference. That's where things can get a little tricky. And that's going to happen, I think, for a lot of the other problems that we're looking at right now because we're multiplying by something here. Okay, 9 to the negative 3a power equals 79. Let's go ahead and log both sides. I'll go natural log both sides this time. 79. Let's go natural log both sides here. Haven't seen that in a moment. So that's negative 3a times natural log of, sorry, I was looking at something else. What did I want to look at? I want to look at how a change of base would look. That's fine. Equals natural, negative 3/8 times natural log of 9 equals natural log of 79. I was going to say lateral log. And we're going to divide both sides by negative 3 times natural log of 9. So that's A is natural log of 79 over negative 3 times natural log of 9. Who cares where that negative goes? The point is the answer will become negative as a result of that. So I'm going to go ahead and approximate that. You don't have to trust that I typed this in the calculator correctly. I'm going to have to trust I typed it in the calculator correctly. And I'm getting negative 0.663 approximately. 6 more problems and then we're done. Can I finish within the hour 30? I don't think I can. I can if I wasn't teaching it. I could finish it in the next 2 minutes if I did. But alas, I'm not. Alright, let's log both sides here. You know what? Let's log base 2 on both sides. Let's see if you still remember how this thing works. If I log base 2 both sides, the 2's automatically cancel. I'm just left with n minus 9 here. So over here, I got to do log of 82 over log of 2. That's going to be that conversion. So n equals log of 82 over log of 2. Well, you know what? Here, let's do this instead. I'll leave the answer written like that, and then we'll know how to write the calculation after. Because this will be helpful for other problems afterward. Man, my handwriting's getting really bad right now. I'm sorry. Log base 2, because here's an exact answer, right? You can write this. Log base 2 of 82 plus 9. That's an exact answer. It is. We did log base 2 of both sides. We added 9 over. What you type in the calculator is going to be log of 82 over log of 2 plus 9. So I'm going to try that. Log of 82, or natural log. Log of 82 over log of 2. Close the parentheses. Plus 9. And I'm going to get 50. Oh, this is an exact answer. I mean, I could round it, but it goes, the numbers stop at some point. Anyway, 15.358. But it actually stops at, it's 15.357552. And then it stops. It's almost worth writing an exact answer when you can. Okay. Anyway, so that's that. I just want to make sure you knew. Now on number 18 here, you have to remember, that's a negative 1 multiplying by that 5. It's not negative 5 to that power. So if I divide both sides by negative 1, immediately you get 5 to the 5b equals 8. Positives. Positives. And as I log both sides there, we'll get 5b times log of 5 equals log of 8. Divide both sides by 5 times log of 5, you'll get b equals log of 8 over 5 times log of 5. Now again, in the calculator, just make sure that that 5 is in the denominator. Excuse me, that when you use the parentheses so that it can multiply by those things properly. And we should be getting 0.258. There we go. 4 more. Yeah, not hitting the hour and a half mark. Subtract 8 from both sides. Negative 4 times 11 to the negative 10x is negative 76. Divide both sides by negative 4. 11 to the negative 10x equals 19. Log both sides. You get negative 10x. I think this is the problem that I did with my kiddos. That 19 just popped in my head after I just said it. Log of 19. And then divide both sides by negative 10 times log of 11. We get x equals negative log of 19 over 10 times log of 11. Okay, here we go. Negative. Whenever I type log thing, I'm just doing natural log, but that's okay. 10 times log of 11. We're getting negative. Whoops, didn't write the negative. Negative 0.123. There you go. Whew. Okay, almost there. All right, number 20. Negative 3 times 8 to the x minus 9 power equals negative 15. Divide both sides, I added 3, sorry. Divide both sides by negative 3. 8 to the x minus 9 equals 5, sorry. I was thinking about I could just write change of base instead of logging both sides each time, but I've gotten so deep into this that I probably should write it this way. Log both sides. You learn why the changes go the way that they do by writing this, I hope. X minus 9, excuse me, yeah. Oh, here we go. So here's important for me to mention. X minus 9 times log of 8 equals log of 5. So notice the x minus 9 is wrapped around parentheses here. I want to make sure that I'm still quantifying it like that. I'm going to divide by log of 8 first, right? I'm going to divide both sides by log of 8 first. So log of 8, like so. And then I got to add 9 to both sides. Whoops, that does not cancel. So we'll have x minus 9 equals log of 5 over log of 8. And then add 9, x is log of 5 over log of 8 plus 9. And if you're uncertain of that, and I'm going to round it here. If you're uncertain of that, keep in mind how we could have done the problem by logging from the beginning. I could have done log base 8 of 8 to the x minus 9 power equals log base 8 of 5. And then here, those would have canceled to leave me with the x minus 9. And x equals log base 8 of 5 minus 9, or excuse me, plus 9. So this is the same thing as that, right? These two are the same thing here, log of 5 over log of 8 plus 9. That plus 9 kind of comes after as a result there. But this is what we're going to have to type in the calculator. So I'm ready for that. Log of 5 over log of 8 plus 9. And we get 9.774. 9.774. A bigger number than we're used to. All right, number 21, subtract 4 from both sides. We get negative 4e to the 8n minus 5 equals 22. Divide both sides by negative 4. You get e to the 8n minus 5 equals negative 22 over 4, negative 11 over 2. I mean, I'll tell you what, we're going to natural log both sides here, but don't live too long on this problem. Can't take the natural log of a negative number. You start getting too deep into trying to get n by itself, where you type natural log, you say I'm getting an error, and you're wondering what you're doing wrong. You're trying to take the log of a negative. By the way, I just said natural log both sides because I wanted to cancel out the e's and do all that stuff. I totally was ready to do that. That was natural for me to do. You can't take the natural log of a negative. Let's just go and just try that one part. Natural log. And there's the other part. There was a fraction. You're like, oh man, that's a fraction too. Who cares? You're not going to do anything with it. Natural log of negative 11 over 2. Non-real answer. Can't do it. Can't do it. Domain errors. Okay. Last one. I got one more problem here. Oh, by the way, no solution. The whole question is, it's not does not exist. It's there's no solution. The question is there any value of n you could substitute into here to make that so? And no, at least not a real solution. Okay, last one. I'm going to add 10 to both sides here. I think this one does have the fraction. 4 minus 5v equals, that's 6. So we're going to divide both sides by 8. And we get 6 to the 4 minus 5v equals 6 over 8. That's 3/4. So 3/4 there. I'm going to go ahead and log both sides here. Okay, so log, like that. And then that'll leave us with a 4 minus 5v. This is going to be the biggest problem. 4 minus 5v times log of 6 equals... Now, if I really wanted to have fun with this problem, I'm going to go ahead and expand... This isn't something you have to do at all. Not at all. But I'm going to go ahead and expand this. This becomes log of 3 minus log of 4. You don't have to do this. You can keep it as log of 3/4 if you want. I'm going to put no fractions where I don't need them. That's me exploring this in the clean-looking way. If you want to do it the other way and just see that you get the same answer, that's totally fine. Just keep it as log of 3/4. Because I have to do a little more work with this. I'm going to divide both sides by log of 6 as I need to. That means this whole thing is divided by log of 6. And then, oh my gosh, we have to do a lot with this stuff still. I mean, you know what else you could do? You could write change of base for both of these parts individually. You know what? Here, let's do this. I'm going to change this back. I'm going to kind of make it like a log of 6 kind of thing. So this is 4 minus... I choose to have fun with this. This is log base 6 of 3 minus log base 6 of 4. I'll use the calculator and do log of 3 over log of 6 and log of 4 over log of 6, right? I'm trying to make the answer look best because otherwise it'll be a fraction with a fraction, and I don't want to do that. Subtract 4 from both sides. Excuse me. Oops. Minus log base 6 of 4 minus 4. And divide both sides by negative 5. So that'll be v equals... Now, I don't want the 5 to show up negative, so I'm going to write these in front. The 4 turns positive. The log base 6 of 4 turns positive. The log base 6 of 3 turns negative. And this is all divided by 5. Yeah, like Mr. Robinson, I wrote something way different. Well, guess what? If we do it all correctly, we should get the same answer. So let's check it out. Let's go to the calculator where I'm going to type. And I'm going to clear the calculator here. I get 4 plus log base 6 of 4 minus log base 6 of 3. See what I just did there? Does that still work? Divided by 5. If all goes well, we should have gotten the same answer. I hope I didn't mess anything up. I should get about 0.936. I know I have an answer key somewhere. I want to see if I can pop it up. It does 4 decimal places on the key. I'm going to look for it right now and just make sure I didn't screw anything up when I was being creative because I don't want to crash and burn on the very last one. Oh, do I have an answer key with me? Oh, wait. I do. I'm looking in the wrong spot. We're done. But I want to see if I got this right. No. Uh-oh. I did do something wrong. Okay, then let me look into that. Because you'll say, Mr. Robinson, we're supposed to be on the same page with that one. Add that to get 6, divided by that to get 3/4. Something weird happened that shouldn't have. Okay, well that is a problem because that isn't the same answer. So I got a little too heavy into that, but it should have been the same. Oh, I know what I did wrong. I typed my log things wrong on this one. Let me redo that calculation. Hold on a second. Hold on. This part should be a 6, and that should be a 3. You can see why we don't want to do those that way. So let's do that again. Is that the answer? No. Oh, both of those are backwards. Hold on. I'm reading my logs wrong. This one's correct, how it was. This one needs to be switched. I'm very sorry, guys. There we go. There it is, 0.832. There it is. All right, 0.832. Okay, now I did it right. And that's why you want to at least write out how your properties work. That's log of 4 over log of 6, not log of 6 over log of 4. So I think I said log base 6 of 4, and then I thought that in my head. So 0.832. Okay, see, I wanted to end on a good one, and that ended up being a bit of a whimper. I apologize for that. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I sure hope that this helped in some capacity, even if I screwed up there at the end. Take care. See you in the next one.